What you are about to see is a tiny system that feels its environment. In this project, temperature comes to life on a 0.96-inch OLED, displayed clearly in degrees Celsius. The sensor I'm using is the LM35. Simple, affordable, and not perfect. Yes, it has around a 1-degree error. But for a hobby project and a solid starting point, it does the job surprisingly well. But this project doesn't stop at numbers. When the room is bright, a glowing light bulb appears on the screen. As the environment gets darker, the bulb fades away and the moon takes its place. This is more than just a display. It's a smart, minimal home thermometer concept built from scratch. Now, let me show you how I created this project. Now we are going to see the circuit and electronic components of this project. First, we start with the OLED. Clock pin, which is SCL, is connected to PB6, and the data pin, which is SDA, is connected to PB7. And its VCC and ground pins are connected to 3.3 volts and ground. For the light intensity, we've used an LDR. One pin of the LDR is connected to 3.3 volts and the other pin is connected to ground via a 10 kilo ohm resistor. In fact, this resistor is the pull-down resistor. Then from this nut here, which is connected to both LDR and the resistor, we've connected this nut to pin PA2 of the microcontroller, which is our ADC pin, one of our ADC pins. And here is our temperature sensor LM35. The middle pin of this sensor is its output. We've connected it to ground via a 100 nanofarad capacitor. In fact, this is a low-pass filter. And the output pin of the sensor is connected to pin PA1 via this green wire. PA1 is also one of our ADC pins, and we read the analog signals via this pin, and then it goes to the ADC. And this little PCB here provides our 3.3 volts and 5 volts and GND. We've already discussed how to design this PCB in Altium Designer, and the link is provided in the comment section. You could plug it in via a USB-C connector, and it provides both 3.3 volts and 5 volts. The 5 volt is connected to USB-C connector directly, and this 5 volts has gone through an LF33, which is a voltage regulator, and provides 3.3 volts for us. Then we are going to see how to prepare the CubeMX file for the microcontroller. In CubeMX, first we need to navigate to System Core, RCC, and I've selected high speed clock to be on crystal ceramic resonator, so that we could connect our microcontroller to external crystal resonator. Next, we need to head to sys, and I've selected debug mode to be on serial wire so that I could program my microcontroller via ST-Link. Then in analog, I've selected ADC1. I've enabled channel 1 and 2. And as you can see, scan conversion mode is enabled. When you select number of conversions and set a number higher than 1 to it, this option is automatically enabled. Regular conversion is also enabled, and I've set external trigger conversion source to timer 1 capture compare 1 event, as you can see here. Yep, I've set rank 1 to channel 1, and I've set the sampling time to 41.5 cycles. Rank 2 is dedicated to channel 2, and the sampling time is also set to 41.5 cycles. Yes, and in DMA settings, I've added ADC1 to DMA, and I've set the mode to circular, so DMA data can be accessed through memory in a circular format. and data width is set to half word and memory is checked. That's it for the ADC, but as you remembered, we've already set the external trigger to timer 1, so we need to configure timer 1. I've set channel 1 to PWM generation channel 1. You would see it here. And I've set the pre-scaler to 8000 and the counter period to 1000. As you can see here, all the timer clocks are set to 16 megahertz, and these 16 megahertz is divided by 8000 and then by 1000, so the frequency that we get is 2 hertz. And I've also set the pulse to 1000 divided by 2. 1000 is in fact our period, so I've set the pulse to 1000 divided by 2. In fact, we are setting the duty cycle to 50%. And there is another thing that I want to tell you, that I've reduced the ADC clock so that the sample and hold capacitor has enough time to charge and discharge itself. And the input frequency is set to be provided by HSE, which is our external high-speed clock. You could see it here, PLL clock. And it is really important. If the ADC frequency is so high and the sampling time is so small, the capacitor of the sample and hold circuit does not have enough time to discharge itself and then do the next sampling. So it is important to keep it short, so ADC channels has the less effect on each other when we are doing the data conversion. And that's it for the timer as well. And in order to be able to connect the OLED to our microcontroller, I've also enabled I2C1. I've set I2C to I2C, and I've also set the I2C speed mode to fast mode, which sets the clock speed to 400 kilohertz. That is the speed of the clock. And then our code is ready to be generated by CubeMX. Next, we are going to see how to write the necessary code for our microcontroller. Now we are going to see how to write the firmware for this project. To do that, we need to head to core, source, main.c. We need to include STM32 It is our OLED driver. We should also include fonts.h. It is used for writing text on our OLED. stdio.h is also included. It is used for a printf function. We should also convert our images into C arrays and then include them in our project. You can see I've included degrees Celsius image, bulb image, and moon image in my project. There are many online tools that convert your images into C arrays, and I've used one of them. Then you should include those images in your projects in this manner. For example, here's the moon.h. You could see in this header file I've included the C array. We need some variables also to write the firmware for this project. The first one is an array of unsigned 16-bit integers. I've called them ADC values. It has two variables, and it stores ADC raw values, which is a number between 0 and 4095. That's because our ADC has 12 bits. I've also created another array called temperature array, and it has 5 variables. In fact, we take 5 samples from the temperature ADC value, and then we calculate the average of these samples and store these values in a variable called temperature. In fact, we are doing a simple low-pass digital filter. This I here is our temperature counter index, which will be used to calculate the average of our temperature samples. We will see its usage in minutes. and another variable for storing the light intensity. We see the ADC value of our LDR and then represent it in a number in percent. And I've also created an array of characters and I've called it buffer. We show our text and numbers on OLED using this buffer. We should also configure our ADC and timer. To do that, we go to our ADC initialization. Here we are. In user code begin ADC1 init2, we start our ADC in DMA mode. You could see I've cast our array into uint32_t variable, and the number of channels is set to 2. We should also configure our timer too. Here we are. In user code begin team1 init2, we start our timer in PWM mode. Then we need to write our code in our main function. Here in user code begin 2, I have initialized our display using the function STM32F103C8T6 and in our while loop, first we show the temperature on our OLED using a printf function to gather numbers and text together, and by using STM32F103C8T6 puts, we show these string on the display. Then we show degrees of Celsius image on our OLED just next to the temperature value, and then according to the light intensity of the environment, we show the bulb or the moon. If there is enough light, we show the bulb on the OLED, and if the environment is dark, we show the moon image on our OLED. After doing all these, in order to keep the data shown on the screen updated, we should refresh the screen. This is done using this function, and we refresh our screen every 1 second. And that is the required code for this project. This is the outcome of this project. At the end of the day, I would like to suggest you not to use LM35 for your commercial projects. For hobby projects, it is totally fine, but for serious and commercial projects, no. If this content was useful for you, don't forget to give it a thumbs up and subscribe to Sly Fox Electronics YouTube channel for more electronic contents. The source code and project files are available in my GitHub repository and the link is provided in the description. Good luck!